So welcome everyone. Welcome to part 4 of this introductory course on partial differential equations. So in this part, we'll talk about the wave equation. Actually, I'm actually going to start with the transport equation first, and then we will get to the wave equation. So recall the transport equation which we considered earlier. So it was ut plus ux, that is du dt plus du dx is equal to 0. So we want to see how we can actually solve this. Okay. So actually, what I'm actually going to consider is an initial value problem. So more precisely, we consider the following problem, that is ut plus ux is equal to 0 in r cross 0 infinity. In other words, it's a real line, upper half plane. Okay, 0 time is the y-axis, so it is 0 infinity, and the initial value I specify to be u of x comma 0 is equal to g of x. Okay, now if I just look at this equation, ut plus ux is equal to 0, what it tells me is that some directional derivative of u vanishes. So I want to exploit that insight. Okay, so how do I actually exploit that? So let me define a new function, which is z of x is equal to u of x plus s comma t plus s. And let's see what we have. So what we have done is, so I have restricted my u to a one-dimensional set. Actually, it's in this case, it's a line. And I want to treat this one variable function z of s. Okay, so if I consider this and suppose I differentiate. Okay, let me just take this over here. Okay, so suppose I differentiate this z of s. So I get z prime of s. So I need to use the chain rule. So I get du dx evaluated at this x plus s comma t plus s. And then I need to differentiate x plus s with respect to s. That gives me 1 plus du dt evaluated at this x plus s comma t plus s and evaluated at the point so the derivative of t plus s with respect to s, which is 1. But I'm given that ut plus ux vanishes in the entire r cross 0 infinity, which means that what we see is that my z prime of s is equal to 0. Okay, so z prime of s is equal to 0. So what it means? So what it means is that if the derivative is equal to 0, that implies that z is a constant. Now, what was this x plus? So what was this motivation for considering this x plus s comma t plus s? So let us see that. So given any point, so I have a picture over here. So given any point x comma t, right? I consider this line, the line. So this line with slope 1. Okay, so this line with slope 1. So that's going to be parameterized by, let's say s is a parameter. So it's going to be in the direction 1 comma 1. And the parameterization is going to be s going to x plus s comma t plus s. So x and t are fixed right now. Okay. Now, as you so what we have actually done is we have restricted our z to the z is defined as u restricted to that line. And what we have shown is that u restricted to this line is a constant. Okay, so u restricted to this line is a constant, which means what it means is that the value of u at the point x comma t is the value of u along every point on this line. But I'm given an initial value problem. In other words, I'm given the function, so the u should satisfy on the x-axis. So on the x-axis, I'm given that it's actually a function g of x. So therefore, since I know the value of u on the x-axis, and that's going to be the same value along every point on this line. That's the interpretation. Okay, so what we observe is that, so the solution of the initial value problem, right? So the initial value problem being ut plus ux is equal to 0 with u at x comma 0 is equal to g of x is actually this u of x comma t is equal to g of x minus t, right? Because when this line is starting at the point x comma t in the direction 1, 1, it actually goes and crosses the x-axis at the point x minus t comma 0. And because I know the value of u on the x-axis, so I have u of x comma t is equal to g of x minus t. Now, let us actually check that this is indeed a solution. Okay, so what we have? So we have that dxu is g prime. G is just one variable function. So g prime of x minus t. Now dtu, I have to use chain rule. So I have dtu is g prime of x minus t times the derivative of x minus t, which is -1. Okay, but because there is a minus sign, now you observe just adding dtu and dxu, you observe that it's actually equal to 0. Also, when t is equal to 0, you see that my solution was u of x comma t is equal to g of x minus t. So suppose I specify t is equal to 0, then I get that u of x comma 0 is equal to g of x minus 0, which is g of x. So therefore, the initial value is also satisfied. So I have solved the initial value. I have solved the initial value problem. Okay. Of course, I'm not specifying certain things over here. So one thing being that some regularity on G is assumed because I'm differentiating, right? So I'm not touching upon those aspects, but this is assuming that there is enough regularity on G. This is a solution. Okay. Now, for with what will follow later on, we also need the non-homogeneous transport equation. So I have ut plus ux is equal to f of x comma t in r cross 0 infinity. And I assume that u of x comma 0, that's equal to g of x. Okay, so you see that there is a non-homogeneous part over here, which is f of x comma t. And I want to solve this also. Okay, so how do we solve? It's the same insight. So let me define z of s is equal to u of x plus s comma t plus s, and then I differentiate. So when I differentiate, I get ux at x plus s comma t plus s plus ut at x plus s comma t plus s. But because this is true for all x comma t in r cross 0 infinity, so the right hand side is going to be now f evaluated at x plus s comma t plus s. So now let's integrate with respect to s, what we get. So what we get is, okay, let me integrate it from minus t to 0, because minus t is the point corresponding to where it actually crosses the x-axis, and I know the initial value. That's the motivation for considering this to be minus t. So I have minus t to 0 z prime of s ds, which by fundamental theorem of calculus, it's z of 0 minus z of minus t, and that's equal to minus t to 0 f of x plus s comma t plus s. Okay, so actually, I'm sorry, this got a little cut off, but pretty much everything is there over here. So z of 0 corresponds to u of x comma t. Okay, and z of minus t corresponds to, what is z of minus t over here? So z of minus t is u of x comma, x minus t comma 0. But u of x minus t comma 0 is given to me because when the t plus s part is equal to 0, I know the initial value, which is g of x. So that's all I have put over here. So therefore, we get the solution in this particular case as well. So z of 0 is equal to u of x comma t, and z of minus t is known. It is actually going to be g of x minus t. So therefore, that comes to the other side, and then I have the solution. Okay. So now let's consider the one-dimensional wave equation. So I have consider r cross 0 infinity, and then I consider utt minus uxx is equal to 0 in r cross 0 infinity. But because there are two derivatives involved in time, I specify an initial value as well as an initial velocity, which is ut. Okay. Now, because this is actually a one-dimensional case, that is, by one dimension, I mean the space dimension is 1. Okay. So that's how we consider the space dimension is what actually we consider. This time is the evolution. Okay, so you have utt minus uxx is equal to 0, but because this is one dimension, I can actually split this utt minus uxx as dt plus dx composed with dt minus dx of u of xt. So it's quite easy to check that this is actually the same as utt minus uxx. It's the same as a square minus b square is a plus b times a minus b. Okay, so now having said this, now what we do is we specify this dt minus dxu as a new function. Let me call it as v of xt. So when I specify that to be v of xt, then what do I have? So in this part over here, I substitute v of xt, and then I get dt plus dx of v of xt is equal to 0. Okay, now not only that, now what is the initial value? So I want to consider an initial value problem. So the initial value is going to be v of x comma 0. Actually, we will be able to specify what is this v of x comma 0 very precisely. So let me go to the next slide. So So we know how to solve this equation. So what we have is, so we have that, because this we saw earlier, right? Remember, if the initial value was g of x, then the solution is going to be v of xt is going to be g of x minus t. But g in this case is going to be v of x comma 0. So therefore, the solution is actually v of xt is equal to v of x minus t comma 0. Now let us actually find this v of x comma 0. Okay, so what is v of x comma 0? Or, v of x comma t was dtu minus dxu. And when I specify t is equal to 0, I get v of x comma 0 is dtu of x comma 0 minus dxu of x comma 0. But you see, I have already specified the initial velocity here. Ut of x comma 0 is equal to g of x. Okay, so that I can substitute. So dtu of x comma 0 is g of x. And dxu of x comma 0, well, dxu is not specified, but u is specified. But because u is specified at the initial time, I can also differentiate along the x direction. So therefore, I get, because u of x comma 0 was f of x, so I get dxu is equal to f prime of x. So I get v of x comma 0 is g of x minus f prime of x. Okay, so therefore, my solution v of xt, which was v of x minus t comma 0, is actually going to be v of x minus t comma 0 is g of x minus t minus f prime of x minus t. Okay, so I have found v now, but my goal is to actually solve for u. And remember, so let me just go back. So my u is actually, u solves this particular equation. So dt minus dxu is equal to v of x comma t. Therefore, you see that this is a non-homogeneous transport equation that we considered, except that there is a minor change. In the earlier example that we considered, I had dt plus dx is equal to some f of x comma t. Here, it's only that dt minus dx is equal to, in this case, v of x comma t. Okay, but if we know to solve for dt plus dx, then we can also solve for dt minus dx. Right. So let's consider the non-homogeneous transport equation, so which is dt minus dxu is equal to v of xt. But we have found that v of xt is actually v of x minus t comma 0, and we have also identified what is v of x comma 0. So therefore, the equation that we have is dt minus dxu is equal to g of x minus t minus f prime of x minus t. Here, right here, and the initial value u at the initial time is equal to f of x. So the initial value of u is f of x. So now I have a non-homogeneous transport equation with the initial value being f of x. I know how to actually solve this. In fact, we found the solution earlier. As I mentioned, it's just that in this case, the sign is changed. So therefore, we just need to slightly modify our z of s. So let's modify our z of s to be u of x minus s comma t plus s. Okay. And when I differentiate this, so z prime of s is going to be what? So it's going to be du dx evaluated at this x minus s comma t plus s times minus 1 plus du dt times plus 1 because of this t plus s factor over here. So in fact, we precisely get dtu minus dxu, and that's the motivation for actually defining this x minus s over here. So I have dtu minus dxu of x minus s comma t plus s. So this is dtu minus dxu evaluated at x minus s comma t plus s. So therefore, the right hand side, which is g minus f prime, also has to be here, right here. So this g of x minus t minus f prime of x minus t also has to be evaluated at the suitable point. Okay, so we get g of x minus t minus 2s minus f prime of x minus t minus 2s. That's exactly what we have. Or in other words, let me just cut out the middle part. So I have z prime of s is equal to g of x minus t minus 2s minus f prime of x minus t minus 2s. Okay. Now, as before, let's integrate. So when I integrate from minus t to 0 of z prime of s ds, so what do I get? I need to integrate the right hand side, which is minus t to 0 g of x minus t minus 2s minus f prime of x minus t minus 2s. Okay. So you see that there is actually an f prime over here. So therefore, you expect that some fundamental theorem of calculus is involved, but you need to be a little bit careful, because first of all, this minus 2s comes with a negative sign, and there is also this minus 2 over here. So what you need to do is you need to actually consider a function and its derivative. So therefore, you need to modify it a little bit so that you can apply the fundamental theorem of calculus. So that's all you need to take care of. So what we have? So what we have is we have z of 0 minus z of minus t is minus t to 0 g of x minus t minus 2s. Now here is where I have modified so that I can actually take the fundamental theorem of calculus. Also notice that I have changed the variable s in 2s as u. So therefore that explains this half over here. And you see that in the earlier part, we had a minus sign. We had a minus sign over here, right? But now it comes with a plus sign because of the fact that now I have put the derivative outside. So therefore, when I apply the chain rule, I get f prime of x minus t minus u times minus 1, so it's compensated. But because now it's the derivative, it's in a form that I can apply the fundamental theorem of calculus. So when I apply the fundamental theorem of calculus, we get something. Okay, so this is what I have explained over here. So we have changed variables to s as u, and also taking care of the negative sign by putting the derivative outside. You see, it's f of x minus t minus u whole prime. Okay, so now we know that z of 0 is u of xt and z of minus t. Okay, so let's see what is z of minus t. So z of minus t is going to be, okay, so t plus minus t, that part goes, and then I get u of x plus t. Okay, so I get u of x plus t comma 0, and then I have minus t to 0 g of x minus t minus 2s ds, and here I can apply the fundamental theorem of calculus. I get half of f of x minus t minus f of x plus t. Okay, but you see that u of x plus t comma 0, so the initial value is actually f of x plus t. So I get u of x plus t comma 0 is equal to f of x plus t. So therefore I have that part there as well. So I get this f of x plus t. Also, what I want to do is I want to change these variables a little bit, because I'm actually going to, you will see in the next maybe 1 or 2 slides as to why we actually do this. So let me just change variables. So let me put x minus t minus 2s as u. And then when you do the change of variable formula, you get minus t to 0 of this part is minus half of x plus t to x minus t. Okay, or I can switch x minus t to x plus t and then get rid of the minus half to plus half, and that's what we have. Okay, so putting it all together, okay, so there is this part over here, this u of x plus t, which is f of x plus t, so that goes to the right hand side. And putting it all together, what we observe is that u of x comma t is half of f of x plus t plus f of x minus t plus half of integral from x minus t to x plus t g of u du. Okay, so now this is what is called as this is the famous D'Alembert formula for the solution of the one-dimensional wave equation. Okay, now there is a very nice interpretation of this formula, which is what I actually want to emphasize. So suppose I want to find the solution of u at the point x comma t. Notice that you see that the value of f at x plus t comes up, right? The value of f at x minus t also comes up. That explains this part over here. And what you have is the integral of the function g. So g refers to the derivative u prime at the time t is equal to 0. So I get half of x minus t to x plus t g of u du. Or in other words, if I want to find the solution at the point x comma t, all that is needed is the following, that I only need to find I only need to know the solution of the initial values f and g between the, so in fact f only at these 2 points is required, and g I need to know for every point between these 2 points, which is x minus t comma 0 to x plus t comma 0. So this x plus t comma, so you consider the slope plus 1 and minus 1, and then you draw the line. So you have this triangle. Okay, and now the point is you can find the value of x, the value at x comma t only depends on the value of the initial value between these 2 points. So now why is this important? Okay, so let us see why this is important. So this is what I just mentioned. So note that the solution of the wave equation at xt depends only on the initial values between the points x minus t comma 0 to x plus t comma 0. Or in other words, what we have is for the solution to the wave equation, we have finite speed of propagation. Okay, so we actually did the infinite speed of propagation in the context of heat equation. So what we have is that if you have the initial value to be non-negative and at one point it is positive, then the solution becomes positive everywhere. But this is in contrast. So that is for the heat equation. And here what we observe is that that's not true for the case of wave equation. So we actually say that this is for the wave equation, there is actually finite speed of propagation. Okay, so compare this. So please go back and then compare this with what we encountered for the heat equation. For the heat equation, if you have a non-negative initial value and if at one point it is positive, then the solution becomes instantly positive everywhere. Whereas it's not the case over here. Okay, so now what I want to do is we can actually extend the method that we encountered. So one-dimensional case is special, of course, but actually the solution to the high-dimensional case also follows from the analysis for the one-dimensional case. It's going to be slightly more complicated, but nevertheless, I want to motivate as to how this actually comes about in the high-dimensional case. Okay, so for the high-dimensional case, what we have is what is called as the famous Euler-Poisson-Darboux equation. So my goal here is to motivate that the solution to the one-dimensional wave equation will come in handy in the high-dimensional cases as well. Okay, so we derive what is called as this Euler-Poisson-Darboux equation. So my goal is the following. So I want to consider the wave equation utt minus Laplace u is equal to 0 in Rn cross 0 infinity. And I have u of x comma 0 is equal to f of x, and then the ut of x comma 0, that's equal to g of x. Okay, and I want to see how this, what we did for the one-dimensional case, modification of that actually comes up in the high-dimensional cases as well. Okay, so you fix an x comma t in Rn cross 0 infinity. I have a picture in the next slide. And what I want to do is I want to consider, so this spherical average we actually considered already in the context of Laplace equation. Okay, so given this x comma t, what I do is I consider, so I have this x comma t, and then you go down to the base t is equal to 0, and then I consider the corresponding point x comma 0. And with that point x comma 0, I draw corresponding to what this r is. I consider a sphere of radius r, and then I consider the spherical average. So remember that t is t is fixed. So t is fixed for the discussion. So in other words, there is no average that is taking place as far as the time variable is concerned. Only in the x variable there is a spherical average. So this is my u of x comma t comma r. Let me just show you with a picture. So I have this x comma t over here. I project it down below. That is this black dot, which is x comma 0, and this is radius r. And then I consider the spherical average of this u, the spherical average of u over this particular sphere, but with t fixed. Okay, so t is like a parameter. So t here is a parameter. Okay, corresponding to this x and r. So the point x specifies where exactly in the base space I have the center, and r specifies how big the sphere is. Okay, and then I consider this dB of x comma r. Okay, so now what I want to do is so now you see that x comma t is fixed. Okay, I want to treat this just as a function of r. Okay, so once we consider this as a function of r, so this is what we have. So you have u of x comma t comma r is the spherical. So this is the 1 over n omega n r to the n minus 1. So it's going to be the reciprocal of the surface area, dB of x comma r, u of y comma t, ds of y. So now what I want to do is I want to differentiate this quantity with respect to r. And now in the context of Laplace equation that we saw, this is the same trick. So what I want to do is, because there is dB of the integration is over a surface which depends on r, so I want to get rid of that dependence, put that as part of the integrand. So the way I do that is I just do a change of variable. And when I do the change of variable, then the Jacobian is going to be r to the n minus 1 ds of theta, where ds of theta is the surface measure on the unit sphere. So therefore the r to the n minus 1 cancels from here. Okay, so I have 1 over n omega n integral Sn minus 1 u of x plus r theta comma t ds of theta. Okay, so now that we have made the region of integration independent of r, now let's differentiate. So differentiating this with respect to r, what do I get? I need to consider du dxi dot with du dxi times theta I, and that summation from I is equal to 1 to n by chain rule. Okay, now notice that this is some expression that we have already seen before. It's actually it's quite parallel to what we did in the context of the Laplace equation. Okay, so now I want to suitably interpret this. So what we can do is we can go back to I just do the reverse change of variables to go back to dB of xr. So when I go back to dB of xr, so I get 1 over n omega n r to the n minus 1. And then here I have gradient with respect to only the x variables. There is also a time variable. Okay, so the gradient is only with respect to the x variable. Dot with, now this theta I is going to be the unit outer, the unit vector. Okay, so the unit vector is going to be y minus x divided. So y minus x, the length of y minus x is going to be r. So when you divide it by r, you get the unit vector. So theta I is the ith component of y minus x by r. And what you actually get here is a dot product. And then you have ds of y. But this is something that we saw before, right? Because now this looks like what we actually get from by applying the Gauss theorem. Okay, but Gauss theorem applied to du dxi. Therefore, I have to consider the double derivative, and then I also have a sum. So therefore, in parallel to what we actually saw in the context of Laplace equation, so you get ur of x comma t comma r is 1 over n omega n r to the n minus 1. So now I use the Gauss theorem, and then I get b of x comma r Laplace u of y comma t dy. And I just want to emphasize that this Laplace is only taken with respect to the space variables, not with respect to the time variable. Okay, so now let's also differentiate this quantity again with respect to r. Okay, so when I differentiate again with respect to r, so I get r of x comma t comma r. So that's going to be equal to, so I use product rule over here. So I differentiate this quantity, right, times this quantity plus now this quantity, the derivative of this quantity with times this quantity. Okay, so what you observe is the following. So, okay, let me just, so I have this 1 over n omega n r to the n minus 1. So when I differentiate, I get exactly this. Times this b of x comma r Laplace u of y comma t dy. Plus now I retain this 1 over n omega n r to the n minus 1. And now what you need to do here is the following. So you change this into polar coordinates. So you have this b of x comma r. You can write it as integral from 0 to r. Okay. And you have db. So the surface db of x comma s. And then I need to use s to the n minus 1 ds of theta, the big S of theta, ds, small s, where s goes from 0 to r. And now when I differentiate this quantity, this is exactly what you get. So you get that the derivative of b of x comma r is the derivative, the integral over the sphere db of x comma r Laplace u of y comma t ds of y. So just I want to emphasize, how do you actually go about proving this? So you write b of x comma r in terms of polar coordinates. So I get integral from 0 to r. And let's say okay, t is taken. So let's consider s as the variable of integration that runs from 0 to r. Okay, so then what do I need to do? I need to consider 0 to r, and then I consider integral over Sn minus 1. Okay, now the Jacobian of the transformation is going to be s to the n minus 1 ds of theta. And then I have Laplace u of, now instead of y, I need to substitute x plus s theta. And now you see that I have an integral from 0 to s of some quantity. Now when I differentiate, the integral sign goes away, and what remains is just integral over Sn minus 1 of some quantity, but I can just bring it back into dB of x comma r. So this requires 2 steps, but this can be, so now that we have enough practice in doing this, so this can be easily filled up, and this is exactly what I have. Okay, now as I told you, utt so the definition of this big U, it's only a parameter. So T is only a parameter. Okay. So therefore, when I consider UTT, I can just take the differentiation with respect to T inside. So I get exactly d square U dt square of y comma t ds of y 1 over n omega n r to the n minus 1, which is what we had in the previous case. Okay. So now it's a simple calculation. So you consider UTT, URR, and then you also have this new expression, which is UR. Okay. So now because of these, you just look at this. You see that you have a d square U dt square minus Laplace U, but that is the wave equation. And that, so any quantity that involves d square U dt square minus Laplace U, that's going to be equal to 0. So therefore, that part vanishes. And then you need to compensate for, you see that you have this UR over here with B of X comma R, and there is also a B of X comma R over here. So this part needs to be compensated with this UR factor over here. And that's exactly what I have. So what we have is that now the big U satisfies what is called as this famous Euler-Poisson-Darboux equation. And this is in R plus cross 0 infinity because R is considered positive. Okay, R is positive. So UTT minus URR minus of n minus 1 by R, UR is equal to 0. Now, notice that when you consider the one-dimensional case, when n is equal to 1, you see that there is no UR part. But you see that this you have this URR minus n minus 1 by R UR. So therefore, now by suitably defining a new function, you can actually define this as the URR of something. So therefore, you see that you actually go back to a version of the D'Alembert formula for the one-dimensional case. So that was my motivation for considering the one-dimensional case in detail. So therefore, you can actually apply that same approach even in the n-dimensional case. But I just want to emphasize one thing, that the even and the odd dimensional cases for the solution to the wave equation are going to be quite different. In fact, what you actually do is you solve the wave equation in odd dimensions, and then based on that, you actually construct the solution in the even dimension. So this is what is called as a method of descent. So this requires a few steps, but you see that the solution that you actually find is motivated by what happens in the one-dimensional case. And this is what I actually wanted to motivate. So thank you very much. The references, if you are further interested in these aspects of partial differential equations. So there are, two very good references. One is partial differential equations by Lawrence Craig Evans, and then a basic course in partial differential equation by Chin Han. Very nice books. These are a graduate level textbooks, but advanced undergraduate students can also take this course, and it's very interesting. It gives a very interesting aspect of partial differential equations. So thank you very much. I stop here.